In the second part of the presentation, I will discuss 10 problem-solving questions regarding noise problems using the discussed noise equations. So in the first problem, it is about noise, FM signal, and phase shift. So the question is, what is the frequency deviation and FM signal to noise ratio? Assume that the signal to noise ratio, which is denoted by S/N, is 3:1, and the modulating signal frequency is 800 Hz. The phase shift is then theta is equal to inverse sine noise to signal ratio, which is equal to the inverse sine of 1/3, which is equal to 19.47 degrees. So the maximum phase shift occurs when the noise and signal phasors are at a right angle to each other, as illustrated in figure 512b, which is here. So this angle can be computed with the arc sine or inverse sine according to the formula theta is equal to inverse sine n over c. So it is possible to determine just how much of a frequency shift a particular phase shift produces by using the formula frequency deviation is equal to phase shift in radians times frequency of modulating signal. So next, assume that the maximum allowed deviation is 5 kHz. So since there is 57.3 degrees per radian, this angle is theta is equal to 19.47 degrees all over 57.3 degrees. So this will be converted into radians, so that will be 0.34 radians. The frequency deviation produced by this brief phase shift can be calculated as the frequency deviation is equal to the phase shift in radians, which is 0.34 times 800 is equal to 271.8 Hz. So just how badly a particular phase shift will distort a signal depends on several factors. Looking at the formula for deviation, you can deduce that the worst case phase shift and frequency deviation will occur at the highest modulating signal frequency. The overall effect of the shift depends upon the maximum allowed frequency shift for the application. So next, we will get the ratio of the frequency deviation and the maximum allowed deviation. So that will be 271.8 Hz divided by the maximum allowed deviation, which is 5 kHz. So that will be 0.0544. So the signal to noise ratio is also the reciprocal of the noise to signal ratio. So we will get the reciprocal of the noise to signal ratio. That will be 1 over 0.0544, which is equal to 18.4. So for FM, a 3:1 input of signal to noise ratio translates to an 18.4:1 output signal to noise ratio. So next problem, this is just an extension of the first problem, which involves noise, FM signal, and phase shift. So we have a similar problem, and the problem goes, the input to an FM receiver has an signal to noise ratio of 2.8. The modulating frequency is 1.5 kHz. The maximum permitted deviation is 4 kHz. So we have to solve the frequency deviation caused by the noise and the improved output signal to noise ratio. So we have all the given here. We will just apply it to these formulas. So first, the angle is equal to the inverse sine of the noise to signal ratio, which is 1 over 2.8, and that will be 20.92 degrees. So converting that into radians, we have 0.3652 radians. So next, the frequency of deviation is equal to the phase shift in radians, which is 0.3652, times the frequency of modulating signal, which is given in the problem. It is found to be 1.5 kHz. So multiplying the two, we will get 547.8 Hz. So that is the frequency deviation caused by the noise. Next, we will get the improved output. So the noise to signal ratio is equal to 547.8 Hz all over 4,000. So that is the maximum permitted deviation. So the noise to signal ratio is 0.13695, and getting that reciprocal 1 over n over s is equal to 7.3. So that is the improved output of the signal to noise ratio. So in the third problem, we have a problem about modulation index. So modulation index is the ratio of the frequency deviation, which is given by MF is equal to FD over FM, where FD is the frequency deviation and FM is the modulating frequency. Sometimes the lowercase Greek letter delta is used instead of FD to represent deviation. So we have the maximum deviation, which is 25 kHz, and the maximum modulating frequency. So dividing 25 kHz by 15 kHz, we can obtain the deviation ratio, or what we call the modulation index, and it is found to be 1.667. So when the maximum allowable frequency deviation and the maximum modulating frequency are used in computing the modulation index MF, is known as the deviation ratio. So next, we have a problem about FM signal bandwidth. So what is the maximum bandwidth of an FM signal with a deviation of 30 kHz and a maximum modulating signal of 5 kHz as determined by figure 5.8 here and by Carson's rule? So the total bandwidth of an FM signal can be determined by knowing the modulation index and using figure 5.8. So the bandwidth can then be determined with the simple formula. Bandwidth is equal to 2 times FM times the number of significant sidebands in the signal. So another way to determine the bandwidth of an FM signal is to use Carson's rule. This rule recognizes only the power in the most significant sidebands with amplitudes greater than 2% of the carrier. This rule is given here. So bandwidth is equal to 2 times the FD max plus FM max. So first, we will get the modulation index, or what we call the deviation ratio, and that is given by FD over FM. And the modulation index is 0.13695, and getting that reciprocal 1 over n over s is equal to 7.3. So that is the improved output of the signal to noise ratio. So next, we have a problem about FM signal bandwidth. So what is the maximum bandwidth of an FM signal with a deviation of 30 kHz and a maximum modulating signal of 5 kHz as determined by figure 5.8 here and by Carson's rule? So the bandwidth is equal to 2 times the FD max plus FM max. we have those parameters in the problem. So 30 kilohertz divided by 5 kilohertz is equal to 6. So by applying Carson's formula, as needed in letter B, bandwidth is equal to 2 times 30 kilohertz to quantity 30 kilohertz plus 5 kilohertz. So the bandwidth is then 70 kilohertz. Figure 5.8 shows 9 significant sidebands spaced 5 kilohertz apart from the MF, which is 6. So the bandwidth is equal to 2 times MF times the number of significant sidebands. So that will be 2 times 5 kilohertz times 9, which is equal to 90 kilohertz. So in the next problem, assume that the signal voltage is 1.2 microvolt and the noise is 0.3 microvolt. Find the signal to noise ratio and express it in terms of voltage in decibels. So if the signal power is 5 microwatts and the power is 125 nanowatts, find the signal to noise ratio and express it in terms of power in decibels. So since we have the two parameters needed, so we will substitute it in this. We will get its ratio. So that will be the signal voltage all over the noise voltage, which is 1.2 all over 0.3, and we can see that they have the same units. So that will be unitless, and the signal to noise ratio is equal to 4. So for voltage, in order to convert it to decibel, we need to we need to substitute the signal to noise ratio in this equation. So 20 log 4 is equal to 20 times 0.602, which is equal to 12 decibels. So next in the power signal to noise ratio, we have the signal power, which is 5 times 10 raised to 6. And the power is 125 times 10 raised to negative 9, which is equal to 40. So for power, to convert it into decibels, we need to substitute the signal to noise ratio in this equation. So 10 log 40 is equal to 16 decibels. So in the sixth problem, we are asked to calculate the noise figure of the amplifier if the signal to noise ratio at the output is 20 decibels. So a 140 mV signal level at the input of the amplifier was observed with a noise level of 7 millivolts. So we are asked to calculate for the noise figure. So in the past video, we discussed about the different noise equations, and the noise figure is given by 10 log of f, which is the noise factor, is equal to 10 log of the SNR input all over the SNR output. So since we know the relationship of SNR power and SNR voltage, then the input signal all over the input noise level is equal to the input signal level all over the input noise level squared with regards to voltage. So we will substitute the 140 mV signal level all over the noise level, and we will square it, and that will be equal to 400. And so for the output SNR, this is equal to 20 decibels. So 10 log of 10, the output SNR. So SNR at the output is equal to 10 raised to 20 over 10. So that will be equal to 100. So the noise figure is then equal to this formula. So we will get first the ratio of the input SNR to the output SNR. So that will be 400 all over 100 is equal to 4. And then converting that to decibels, we have 10 log of 10, 4, then that will be equal to 6.0206 dB or decibels. So 7. An amplifier operating over a range of 10 MHz to 28 MHz has a 400 ohm input resistance. It is operating at temperature of 250 kelvins, has a voltage gain of 300, and has an input signal of 80 mV RMS. So we are asked to determine the RMS output voltage signals, the desired and noise, disregarding any external sources of noise. And we are also asked to calculate the signal to noise ratio at the output and express it in both unitless and in decibels. So the given is the input voltage RMS, which is equal to 80 millivolts, and the gain, which is equal to 300. So that is the voltage gain. So what is the output voltage? So we know that the gain is equal to V out over V in, which is the output voltage over the input voltage, and therefore the output voltage is equal to input voltage times gain. So 300 times 80 is equal to 2400 millivolts or 20.4 volts RMS. So the signal level output all over the noise level output is equal to V out RMS all over Vn RMS, where Vn is the noise voltage. So we know that the noise voltage is equal to square root of 4 times Boltzmann constant times the temperature in kelvins times the bandwidth times the resistance. So we have the given parameters here, and substituting that into the equations, we will get V sub n, or noise voltage, is equal to 9.67 times 10 to the negative 3 millivolts. So applying that in this formula, which is V out over Vn, we get 2400 all over 9.67 times 10 to the negative 3. And the signal to noise ratio will be 2.48 times 10 raised to 5. So converting that into decibels, we need to apply this SNR to this equation, 20 log 2.48 times 10 raised to 5. And that will be equal to 107.89 decibels. So in problems 8 to 9, we are asked to solve 3 parameters. So the noise factor of an amplifier is 7. Calculate the noise figure the equivalent noise temperature and noise density. Assume 290 kelvins for the environmental temperature. So in this problem, we will use the discussed noise equations, which are the noise figure, equivalent noise temperature, and noise density. So the given is the noise factor, which is 7. So letter A, computing for the noise figure, we know that noise figure is equal to 10 log 10 of the noise factor. So substituting 7 into that equation, we will get noise figure is equal to 8.451 decibels. And letter B, we are going to get the equivalent noise temperature. So substituting the environmental temperature, which is 290, and the noise factor of 7 into this equation right here, we will get 1740 kelvins. And lastly, for the noise density, we know that it is equal to Boltzmann constant times the temperature. So Boltzmann constant is equal to 1.38 times 10 to the negative 23 joules per Kelvin. So substituting that into the equation, we will get 2.402 times 10 raised to negative 20 watt over hertz. So in the last problem, a diode generator is required to produce 5 microvolt of noise in a receiver with input impedance of 75 ohms. If the generator will operate at 200 kHz, what must be the current through the diode? So here we will use the Schott noise equation, which is denoted by I sub n. So I sub n is the RMS noise current in amperes, and that will be equal to the square root of 2 times the bandwidth over which the noise is observed in hertz, times the DC bias current in the device in amperes, times the charge of an electron. So the given is the noise voltage, the resistance, and the bandwidth. So applying that into the equation, first let us get the IN, which is the Schott noise, which is the noise current rather. That will be IN is equal to P sub n over R. So the V sub n, or the noise voltage, is equal to 5 times 10 raised to negative 6, and the resistance or input impedance is equal to 75. So getting that, dividing that, we get 0.0666 times 10 raised to negative 6 amperes. So we know the RMS noise current in amperes, and manipulating the equation, the Schott noise equation, we can get the current through the diode, which is denoted by I naught. So this is equal to IN squared, or the RMS noise current squared, times Q, all over 2 times Q times P. So Q is the charge of an electron and P is the bandwidth. So Q is equal to 1.6 times 10 raised to negative 19 coulombs. So substituting the values or the parameters, I sub n, which is obtained using V sub n over R, and the charge of the electron and the bandwidth into this manipulated Schott noise equation, we can get the current through the diode, which is 69.44 milliamperes, or 0.06944 amperes. So that is all for my presentation. Thank you for listening.